Hello everyone, my name is Mohammad Anam and I am a master's student at Center for Information Technology in Building Science Lab at IIIT Hyderabad in India. Today I am giving a presentation on the development of Smart Glazing Simulator tool based on the paper SGLSim tool for Smart Glazing Energy Performance Analysis. The outline of the presentation is that I'll start by explaining the motivation behind the study. Then I'll introduce the problem as well as set the objectives of the study. I'll further describe how the tool is working and what are the different set of parameters which are used as an input to the tool. A case study of a city in India is done with the help of SGLSim tool, the results of which are presented and discussed. Finally, I'll give the conclusion of the paper. With the increase in population and urbanization, the world annual energy consumption continues to increase, which leads to increase in the release of harmful gases in the atmosphere. Furthermore, as per the data of EIA, the building sector is responsible for more than one-third of total energy consumption. Hence, there is a strong need to increase the building energy efficiency and to develop new technologies which can satisfy the energy demand and minimize the risk it poses to the atmosphere. Building energy consumption depends on the electricity consumed in heating, cooling, lighting, and other appliances. Window regulates a significant percent of the total energy consumption of the building. Newer innovative technologies such as building integrated photovoltaics, dynamic blind, and electrochromic glazing have been deployed in building facades or windows to conserve energy and maintain occupants' thermal and visual comfort. The performance of smart window system depends on the glazing's optical, thermal, and electrical parameters, along with window orientation and WWR. These properties affect the building energy demand, and in case of the semi-transparent photovoltaic system, it affects the power generation capabilities of the module. Conducting energy performance analysis requires proficiency in the building simulation, which is repetitive and error-prone. A miscalculation in any energy simulation step can drastically alter the results, hence there is a need for a tool. Building integrated photovoltaics are photovoltaic materials used to replace conventional building materials in part of building envelope such as skylights, facade, roof, etc. It empowers building to create part of their power needs while performing engineering functionalities. The STPV is a type of BIPV installed in window that allows a percentage of light to enter the indoor space, which can impact the cooling and lighting load inside the room. It is a modern attempt to merge the demand for energy-efficient glazing with renewable energy. Building integrated semi-transparent photovoltaics innovation has drawn many consideration worldwide due to its noticeable benefit in environmentally friendly power generation. Many studies have suggested the benefits of the STPV facade on building energy efficiency. Electrochromic glass is an electronically tintable glass used for windows, skylights, facade, and curtain walls. EC glazing can dynamically control the heat gain of the window by changing from fully clear tint to dark tint. It is a smart solution for buildings in which solar control is a challenge, such as classroom, healthcare, commercial offices, and retail spaces. The benefits of EC glazing is that it can reduce the peak electric load and provide additional daylighting benefits, improving the productivity and the comfort of the user. It also provides access to daylight and outdoor views, which are linked to faster rate of learning and patient recovery. Buildings that use daylighting as their primary light source and rely on electric lighting only when necessary saves up to 60% on annual lighting energy. Daylighting has numerous advantages for human beings other than energy saving. It impacts human psychology, productivity, and occupant satisfaction. The space designed for daylighting will need blind due to occasional glare and excessive daylighting. Blind controls the amount of sunlight entering the room. Blinds affect the interior lighting load, space heating, cooling loads by regulating the quantity of daylight and incoming solar radiation via the window. Depending on how it is mounted on the window, blinds can be classified in three categories: external, internal, and intermediate. There are two kinds of blind control: static and dynamic. Static blind control is always on or off and manually operated by the occupants. A dynamic blind control allows the control of the blind based on room dynamics. Energy Plus allows different control types for the blind based on solar radiation, slat angle, outdoor temperature, glare, etc. The objective of the study is to develop a parametric simulation-based method to evaluate the energy performance of the smart window, as well as to compute, analyze, and assess the impact of smart glazing on the net annual electricity consumption of the building. Another objective is to perform comparative energy analysis of smart glazing with traditional glazing while varying envelope variables, WWR, and orientations. Finally, to make the task of performing parametric simulation effortless, a tool has been developed for several types of smart glazing such as electrochromic, STPV, and STPV with dynamic blind. The methodology of the simulation depends on the overall energy performance, which has been assessed in terms of electricity benefits. The net annual electricity consumption of the building depends on electricity generation and consumption, as it is a summation of all the electricity generation and consumption in the building divided by the floor area. However, the values corresponding to the electricity consumption are positive, whereas the electricity generation is negative. In each simulation, the tool computes the net annual electricity consumption of the room having a window system such as electrochromic, STPV, and standard glazing with a certain configuration and orientation. The lower the net annual electricity consumption value compared to the baseline, the better the glazing performance. A smart glazing simulator is designed to perform energy performance analysis of STPV, electrochromic, standard glazing, and any of these glazing with dynamic internal blinds. The general workflow of the tool is that any user can sign up and validate his/her email address. After validation, they can input the simulation parameters, which get stored in a task queue. The simulation server, if it is idle, will pop the user input and generate the input data file necessary for Energy Plus simulations. After generating those files, the simulation server starts performing annual energy simulations. The net annual electricity consumption are extracted from the HTML files generated after each simulation and stored in a list, which is then used to generate graphical visualizations. Finally, the simulation server sends the result back to the user. The user interface of the tool is as shown in this slide. As you can see, there are two kinds of parameters, fixed and variable. The building name, location, type, HVAC type, floor area, height, daylight control, and blind control are some of the fixed parameters in the simulation. Whereas orientation, WWR, glazing, optical, thermal, and electrical properties are all variable parameters. This slide shows the features of the tool, which was developed as part of the research. The SGLSim tool is developed on Flask framework and has worldwide weather data. The current tool has task queues and can handle simultaneous request handling, meaning two or more users can simultaneously request for the simulation. It uses EMS for electrochromic modeling and has both heating and cooling loads. It also allows modeling of STPV and gives the option of dynamic blind modeling to the user. Currently, the annual energy simulation are performed on Energy Plus version 9.2. The next part of the research was to conduct a case study in Kolkata, India. Kolkata has a warm and humid climate with hot and humid summer and pleasant winter. The Bay of Bengal heavily influences the climate of the city. The annual mean temperature is 26.8 degrees Celsius, and monthly mean temperature ranges from 15 to 30 degrees Celsius. Summer has a monthly mean temperature of 30 degrees Celsius, but the maximum often exceeds 40 degrees during May and June, whereas in winters the temperature dips to 9 to 11 degrees Celsius between December and January. Rains brought by the Bay of Bengal lash the city between June and September and supplies the city with most of its annual rainfall. These are all the fixed and variable parameters data used in the simulation model for the case study. A square office room with length and width 10 meter and height 3 meter was modeled in Energy Plus. The HVAC installed in the model was ideal load air system and the daylight control is kept on with continuous dimming control as control type to save electricity. The shading control is kept off. The variable parameter was orientation and WWR with 4 primary orientation and 18 WWR points. The window type consists of STPV glazing, STPV with dynamic internal blind, electrochromic glazing, and standard glazing. This graph shows the energy performance analysis of a building with STPV glazing and standard glazing having the same optical and thermal property in the 4 primary orientation in Kolkata. I'll first start by explaining the curvature of the graph and what it represents. All the graph has U-shaped curvature since with the increase in WWR, the net annual electricity consumption initially decreases. This happens because with the increase in WWR, the daylighting inside the room increases, and since the lighting control is set active, the artificial lighting reduces, thus reducing the annual electricity consumption. But after a certain WWR, the annual electricity increases because the increase in cooling load is more than the decrease in lighting load, thereby increasing the net annual electricity consumption. In case of STPV, along with lighting load reduction, the energy generated by PV also reduces the net annual electricity consumption, and hence it shows that higher WWR is possible for STPV system. It also shows that the STPV system is efficient compared to the normal glazing. The lowest net annual electricity consumption was achieved in the north orientation because the solar radiation in the north is less than other direction, thus reducing the cooling load. The comparative energy performance analysis between standard glazing, STPV glazing, and STPV with dynamic internal blind is shown in this graph. The red represents the standard glazing, blue represents the STPV glazing, and green represents the STPV with dynamic internal blind. The optical and thermal properties of all the glazings are same, with electrical properties added in case of STPV and electrical properties with dynamic blind added in case of STPV with dynamic blind. In all the 4 directions, the glazing with glare control dynamic internal blind can save up to 14% net annual electricity consumption compared to standard glazing and up to 5% compared to the STPV glazing. The comparison between the energy performance of a standard glazing and electrochromic glazing is shown in this graph. The red represents the standard glazing and black represents the electrochromic glazing. In all the 4 primary orientation, the electrochromic glazing performed better than the standard glazing. The electrochromic glazing can save up to 5% net annual electricity consumption compared to the standard glazing. The conclusion of the study is that SGLSim tool has been developed for ease in computation of energy performance analysis of smart glazing. Some of the benefits of the tool are the optimal window to wall ratio and orientation can be calculated easily for different glazing systems for a selected city. It reduces the time taken to perform parametric simulations of various glazing systems as the program automates the entire simulation process. It reduces the error in various calculations such as window to wall ratio. It provides the user with graphical results and it is accessible to the end user. With this, I conclude my presentation. If anyone is interested to connect with me, I have provided the QR of my social media sites. Thank you.